Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to compare parametric and non-parametric models. The motivation is that we have learned two ways of estimating the PMF of a discrete random variable that models a certain quantity. The first approach was very simple. We just directly use the empirical probability that that quantity equals to each of its possible values, and that's the empirical PMF. The second approach was a bit more complicated. We basically made some assumptions about the data. We derived a parametric model that only depended on a small number of parameters, and then we fit those parameters using maximum likelihood. In comparison to the second model, the first type of model is often called a non-parametric model because we don't have a model that depends on a small number of parameters. Now the question is, which of these models is better? So our goal is going to be to learn how to evaluate models in realistic situations. The prerequisites for this material are discrete random variables and maximum likelihood estimation. Okay, so let's go back to this free throw data set where we're trying to model the length of streaks of free throws by Kevin Durant. So what's the probability that Kevin Durant makes 10 free throws in a row, or 5 free throws in a row, or 2 free throws in a row? Our data are 377 streaks from the first 3,000 free throws shot by Kevin Durant in the NBA. Our non-parametric model was just the empirical PMF of those data. And our parametric model was a geometric model derived under some independence assumptions where we assumed also that each free throw has the same probability of going in, and that probability is theta. And we saw that when we apply maximum likelihood to this model, our estimate of theta is actually very reasonable. It's just the fraction of made free throws. Okay, this is how the two models look like. And now we want to think about how to estimate them. Okay, so here the parametric model are the circles. Notice that it's a nice geometric curve. And the empirical PMF is much noisier. These are the observed empirical probabilities. There are these black dots. Okay, so how do we evaluate this model? Our first, maybe our first gut reaction could be, well, what approximates the data better? What do we mean by approximate the data here? We want to approximate the probabilities, right? We don't know the true probability that Kevin Durant makes 10 free throws in a row, but we can, look at what fraction of times that happens, and that gives us the empirical probability of the 10 free throws that he has made in a row. So we could compare that to the two models. What is the problem with this? Or, what's going to happen when we do that? Again, pause for a moment and think about it if you want. Well, what's going to happen is that I have just described the empirical PMF of the data. So under that metric, the empirical PMF is going to be amazing. It's, we're comparing it to itself, so zero error. So what's the problem with this? The catch here is that we're using the same data to fit the model and to evaluate. Okay, it's as if we have an exam and I put in the exam exactly the same problems that we had in the homework. You might just memorize all the solutions, put the solutions, and it could seem that you understand everything, but maybe you don't, right? You cannot use the same data to fit and evaluate the model. We're going to make this more precise later on, but that's the intuition. So that's no good. Instead, what we could do, okay, so you cannot use the same data to fit and evaluate the model. Instead, what we could do is we could say, okay, so we don't have ground truth. That's problematic. So how about we come up with some synthetic data where we do have a ground truth and we see, which model is better. So in particular, we could simulate data assuming this parametric model, which sounds quite reasonable for how, free throws could be generated. We can set a theta to a certain value, 0.875. And then we can simulate some IID free throws and compare how both estimates do compared to the true PMF, because in this case, we will know the true PMF. We can go ahead and do that. And what we see So here, the true PMF is this black line, the empirical PMF are the black dots, and the parametric model are the circles. So the circles are almost on top of the line, whereas the dots are a little bit all over the place because of these fluctuations that we expect in empirical probabilities. And in fact, the theta estimated by the parametric model is awesome. It's almost exact. So here the parametric model looks amazing. And if we repeat with 3,000 other free throws, again, much better than the empirical PMF, much better than the empirical PMF. Okay, we've repeated this 3 times. So are we done here? Should we conclude parametric model much better? Let's move on with our lives. No, there's another catch here, which is that the parametric model does not necessarily reflect what's going on in the real data, right? Because if it does, then of course use the parametric model, but this will never be the case. Okay, in real life is much more complicated than the assumptions that we've made to derive the parametric model. We had, for example, assumed that each free throw has the same probability, which had assumed independence between free throws. This is for sure not true in practice, as we had discussed. So then what do we do? These 2 strategies that we have looked at do not seem like a very good idea. Although, by the way, this second strategy of simulating data is always good, as an auxiliary way of checking out models, especially if you have a good grasp of the generating process for your data. Anyway, so then how should we evaluate in practice? What we should do is we should take real data, okay, not like in strategy number 2, and the data should be held out, not like in strategy number 1. Okay, so we cannot use the same data to, as I said, to fit the model and to evaluate, and the data that we use to evaluate should be real. Okay, and that is a crucial idea in statistics and machine learning that has enabled us to make huge progress in developing better and better methods. The idea is that you say, okay, I'm going to divide my data into a training set that I'm going to use to fit or train. People from machine learning like to say train the model. And I have a separate test set that I'm going to use to evaluate, or people in machine learning like to say test the model. And the test data is completely separate from the training set. The model should never see the test set until you evaluate. Okay, so in our case, what we're going to do is we're going to use the first 3,000 free throws shot by Kevin Durant as a training set and the following 3,000 as a test set. And in order to evaluate how well we're doing, we're going to compare the estimated PMF, the PMF estimated by the parametric model and the non-parametric model. Here I'm representing estimated PMF by P sub est, and the empirical PMF that we observe in the test data. Okay, we're going to take the square difference, take its average, square root. That's going to be, it's basically just the difference between the empirical PMF of the test data and our estimated PMF. Of course, what we would really want to do is to compare to the true PMF, because the empirical PMF of the test data is also going to be a bit noisy. But this is all we have. Okay, and it's definitely much better than using the data that we have used to fit the model. Okay, so let's take a look at how the non-parametric model does. And here you can see that both the empirical PMF estimated from the training data, which are the white circles, and the test empirical PMF, which is what we would like it to approximate, they all fluctuate, and they're kind of close to each other, so it's not a bad estimate, but they're definitely not on top. The estimate is definitely not perfect. So this inspires some comments on the advantages and disadvantages of non-parametric models. The first thing to say is that the name non-parametric is a little bit confusing, because it might sound as if you don't have to estimate parameters to fit this non-parametric estimator. But that's not true. Of course, we're estimating stuff, right? In particular, we're estimating the probability of each of the entries of the PMF. So we're actually estimating a lot of numbers. We're in fact estimating a lot of parameters. If we assume that the maximum number of the maximum length of the streaks is 55, we're actually estimating 55 parameters. And the only constraint is that all these probabilities have to add up to 1. no other constraint. So the estimator has a lot of flexibility to fit the training data, which can be really nice. Like, this is actually the good news, is that you have a lot of flexibility to learn any pattern that could appear in the data. That's good. The bad news is that you have also a lot of flexibility to overfit fluctuations that appear in the data. And we have already talked a lot about how, because of limited data, you are going to have noisy fluctuations in the data that you use to fit the models. By noise here, what I mean is fluctuations that are only there because of spurious reasons, because you have limited data, because something weird happened for this data that you're fitting, and you don't expect it to happen in this held out data. You don't expect it to reflect the true structures that you want to model. Okay, that's what's called noise. In contrast to noise, the part that we want to model, the part that we think is going to be preserved between the training and the test data, that's called the signal, usually. So the problem with non-parametric models is that they have a lot of flexibility to fit the signal, but they also have a lot of flexibility to fit the noise. And when we look at the results, we realize that here, the empirical PMF is going up and down. Here, for example, that is not really signal. That is just noise due to the limited data. And in fact, it's not reflected. Like there, the pattern of the test data is completely different, right? It also has its own fluctuations, but they're different from the fluctuations in the training set, indicating that we're overfitting the noise. Actually, I went a little bit quickly there. I forgot to talk about overfitting, which is really important. When you learn noise, when you fit the training data so well that you're also incorporating these noisy fluctuations into your model, that's called overfitting, because you're fitting too well. Okay, and the problem with non-parametric estimators is that, or in general estimators that are models that have a lot of flexibility, a lot of parameters, their problem is that they have the flexibility to overfit the noise in the training data. And this is essentially what happens here. Let's take a look at the parametric model. Remember that the parametric model depends on a single parameter. So we see that it has like this really smooth shape. It does not try to follow the small fluctuations in the training data because it can't. It's completely constrained to have that shape. When we vary theta, the shape kind of stays the same. I mean, it changes a little bit, but it can become more like this or more like that, but it cannot account for these rapid fluctuations. That is something that characterizes parametric model. They have to follow this predefined shape that doesn't allow them to overfit easily. So that's the good news, right? If there's like some weird noisy fluctuations, the parametric model is not going to be able to overfit them. But the bad news is that if there is some meaningful structure that is not captured by the assumptions that you made when you derived the parametric model, you're not going to be able to capture it. And that is called underfitting, when you don't fit the training data well enough. As a silly example, imagine that this actually was real. So there should be a bump here because maybe Kevin Durant really likes the number 11 and he just wants to make 11 free throws in a row and then he doesn't care anymore. Of course, that's not the case. But imagine, if you have enough data, the non-parametric model would probably pick that up. But the parametric model can't because we haven't made that assumption when we designed it, and it just wants to have this geometric shape, so it wouldn't be able to incorporate that additional structure. So again, you pay because you don't have as much flexibility, but you don't overfit, which can be really useful. And in fact, in this case, the test RMSE is better than the one of the non-parametric model. Here we have gained by doing careful modeling and choosing this parametric model. However, maybe if we gathered more and more and more data, the non-parametric model would eventually become better, and we're going to illustrate that with a different data set. In general, but before I move on to that, because I forgot that I had this slide in between, and this is pretty important, our conclusions our conclusions that follow from this discussion of the advantages and disadvantages of parametric and non-parametric models are the following. If you don't have a lot of data, but you have a good knowledge of the data generating process, you can make some assumptions that you are pretty sure are going to be good. What kind of model should you apply? You should apply parametric modeling. What if you have little knowledge about the data generating process, but you have a lot of data? Then you should apply non-parametric modeling. Of course, what happens in practice, the devil is in the details, is you're not completely sure, how much data you have with respect to the complexity of your model. You may not be sure about whether your assumptions hold or not. Then you just need to use held out data to verify all of these hypotheses and evaluate your models. Okay, you should do it in a data-driven way. Okay, so let's come to that example that I just promised you. We're going to use a public data set that I'm going to link in the descriptions, and I'd like to thank the people in Technium who made this publicly available. The idea is that they gathered calls that were received by an anonymous bank over a year. And we're going to imagine that the bank hires us and says, okay, we want to decide how many people should be answering calls. So we want to know what's the probability of receiving different numbers of calls between 6 a.m. and 7 a.m. on weekdays. Okay, that's our task. So this is just, we can represent that by a discrete random variable. What's the PMF of the random variable that represents the number of calls between 6 a.m. and 7 a.m. on weekdays? We're data scientists, so we're going to decide on a training set and a test set. We're going to use 6 months to train our models, from January to June. And we're going to use a test set from July to December. Here, by the way, some of you might be saying, but Carlos, this makes no sense, right? Because you're using different months to train and test, and maybe something is going on in those months. That is true. But this, first of all, this is just an example for the class. Second of all, this is always going to happen, and that's something you have to be mindful about. And you have to design your test set in the best possible way to reflect how you're going to apply the models in practice. So the short answer would be, yes, you're right. Like, we should use maybe the next year if we had it, but I didn't have it. There's only 1 year of data. And yes, hold that thought and apply it when you are designing test sets in practice. That's actually really, really important. Deciding a good test set may be one of the most important considerations when you're doing data science in practice. Okay, so first, we already know what non-parametric model we're going to apply. That's really easy. We're just going to apply the empirical PMF. Let's derive a parametric model for this data. The assumptions we're going to make might sound a little bit familiar. We're going to assume that all the calls are independent, meaning that people calling to the bank, but like these calls are not actually dependent in the sense that if I receive a call now, I'm more likely to receive a call soon. Or if I receive a call like in a particular day, then that day I'm more likely to receive more calls. Okay, just people are, go about their lives, they're calling the bank independently. This might be broken if suddenly there's like a financial crisis and everyone starts calling the bank. Okay, we're going to assume that doesn't happen. People just call the bank independently. Then we're going to assume that if we think of this hour, okay, where we're modeling the number of calls, if we look at a small interval within that hour, a small interval, the probability of getting a call in that small interval is proportional to the length on the interval and to a fixed parameter lambda, which is the parameter that we're going to estimate in our model. And that parameter is going to capture the rate of calls that time of the day. Okay? So we're going to assume that the probability of a call within this very, very small period is lambda t, and we're also going to assume that the probability of having more than one call within that small interval is 0. So what is the parametric model that we could apply here? And if you remember, these are exactly the same assumptions that we made when we derived the Poisson model. Okay, so this just, this justifies a little bit what I was saying, that Poisson models can be used in very, very different situations. They are often used to model arrival of calls or arrival of packets in a router or arrival of emails. Under these assumptions, right? Like people are calling in independently and there's a certain rate. So the way you should think about this parameter lambda is they're like, 23 calls per day, roughly speaking, and the calls arrive independently. Okay, if you make those assumptions, you end up with a Poisson PMF. We saw that it's a little bit more complicated like that, right? Like you derive that it kind of looks like a binomial, and then you take the binomial to the limit, and you end up with a Poisson. You can go check the videos on parametric distributions, the video on parametric distributions if you're interested. Anyways, I will stop rambling and I'll get on with this. Now we have a likelihood for our data. We basically are going to plug in the Poisson distribution there. Of course, we don't know lambda. We want to estimate this parameter lambda from the data. Okay, that's what the Poisson distribution looked like. This is what we derived. Now, we often work with the log likelihood. The log likelihood looks like that. Okay. And now what we're going to do is we're going to maximize the log likelihood because we want to set lambda to maximize the probability of the observed data. When we maximize the log likelihood, we're maximizing a 1D function, in this case, a function of lambda. So what we do is we looked at the derivatives. The derivative of log of lambda is just 1 over lambda. The derivative of lambda is just 1. And this guy is just a constant. So the derivative is the sum from 1 to n of xi over lambda minus 1. I'm also going to look at the second derivative to see what shape this function has. The second derivative, remember that derivative of 1 over lambda is just minus 1 over lambda squared, is actually negative because all of the data are non-negative. This is nice because it means that the log likelihood looks like that, and we can find the maximum by just seeing where the tangent to this curve is constant, which means that the derivative is 0. So we just set the derivative to 0. Remember that this is inside the sum. So this means that we have the sum of the xi's divided by lambda minus n. So the maximum likelihood value of the parameter is equal to the total number of calls divided by n. It's just the average number of calls which corresponds to this intuition that I explained when we were setting up the assumptions for the parametric model, which is kind of like the rate of calls in a way. So it's always good to verify that what you obtain through maximum likelihood or whatever other method corresponds to what that parameter represents in your model, that's a reasonable choice, because otherwise you might have made a mistake. Here, this is pretty reasonable. Okay, so we do that. We train. What I'm going to do here, actually, and this goes back to the point I was making earlier, we're going to see how the parametric and the non-parametric models compare if I use different amounts of training data. So here I'm only using January to train the model, the parametric model. And what I get are these circles. And we're comparing it to the test empirical PMF. The test empirical PMF is obtained by just looking at the empirical probabilities from July to December, okay, in the 6 last months of them, 6 last months. And what we see is that, well, you know, the estimate is not bad, but maybe it's not amazing, right? Like it does like this, whereas the true PMF does roughly like that. But we're only using 1 month of data. So as we use, here we're using 3 months, the estimate is better. You know, this is getting closer. And we use 6 months, it's much better. Okay, so it actually approximates the general shape pretty well, which indicates that we made a good choice of assumptions. The Poisson model here is actually pretty reasonable. In general, we see that the parametric model, as we expect from parametric models, has a certain shape, okay, which doesn't allow it to overfit the data. And that's good, but it might also not have the flexibility to account for some structure in the data that might be of interest. Okay, so now let's look at the non-parametric model. And this is pretty interesting. So essentially what we're seeing is the fractions of times that we observe 0 calls, 1 call, 2 calls, etc. in the training data. Okay, that's what these circles are. And what we see is that in January, when we only use January, we have a lot of days that have 0 calls. Okay, and that actually does not happen at all in the test data. So what I conjecture here is that maybe January had a lot of days which were holidays for some reason. And then in the test data, we don't have January in the test data, right? So So there's this discrepancy, and in this case, we can view this in two ways, right? On the one hand, the non-parametric model has overfit the training data, because this weird circumstance that there are some days that are holidays, so maybe 0 is special in some way. It can account for it. I mean, it accounts for it directly, but it doesn't appear in the test data. So we have overfitted it. It kills us, basically. It will make us have a really bad performance. However, you could also argue that what if you had used test data where there's also January, like of the year after or something? Then this would actually might have been an asset. Because if we go back to the parametric model when we were using only January, we know that the training data was up here, but the Poisson distribution has to have this shape. So because of the remaining training data points, it could not overfit this guy. It couldn't do it. It has to preserve the Poisson shape. It cannot overfit that guy. So in this case, the parametric model enables you to not learn about these holidays. This is good for the test set that I chose, but if I had chosen another test set, this would have been underfitting because it doesn't allow you to learn that structure. And it's okay that it doesn't allow you, right? Because in our assumptions for the parametric model, there were no holidays. If we included the possibility of having a certain fraction of days that always have 0 and include an additional parameter for that, then we could have fit it with a parametric model. Okay, let's continue looking at how the non-parametric model does. It's a bit of a disaster because of this issue when we only have January. And in general, like you can see that it's all over the place because we just don't have a lot of data. And we have already explained that non-parametric models, when you don't have a lot of data, they suffer. As we gather more data, this is for 3 months, and then for 6 months, it becomes much, much better. And in particular here, it starts kind of approximating like some of the structure that we see in the real data. And when we compare both models side to side in terms of test RMSE, we actually see what we had indicated before. This is the number of months that we have in the training set. When we have very little data, the parametric model absolutely crushes the non-parametric model. It's really much, 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 much better. Especially given that in this particular data set, January seems to be a bit weird. It has this issue where like there's a lot of days where there are no calls, maybe because there are holidays. As we gather more data, the non-parametric model improves dramatically to the point where when we have 6 training months, it's already better than the parametric model. So imagine that you had a few years of data, the non-parametric model would probably be better, essentially because it has the flexibility to find signal that is not accounted for in the assumptions that we made when designing the parametric model. The parametric model is able to use additional data, but doesn't make such a huge difference. It's super, super stable. And that is an asset when you don't have access to a lot of data and your assumptions are approximately true. But it also limits its possible performance when you gather more and more data. Okay, so what have we learned? We have learned how to evaluate models in practice. The bottom line is you have to use real held out data. And we have learned about the advantages and disadvantages of parametric and non-parametric models. Parametric models have constrained shapes that enable them to not overfit the noise in the data, but limit them so they could underfit the signal. Non-parametric models have a lot of flexibility, so they can, unfortunately, they can overfit the noise, but they also have the flexibility to learn more structure from the data. So if you have a lot of data, they can have a lot of potential. Thank you very much.